Alright, let's work with some of the equations in simple harmonic motion. And I'll give you a review from the last video. Let me rearrange this a little better. From the last video, I gave you Hooke's law. And Hooke's law is F is equal to negative K. And I gave it to you as X in the last video, but I think I'm going to switch it to A standing for amplitude. And again, that's still how far it is stretched or compressed from equilibrium. And you'll see why in just a moment. Okay, well, when I put some energy into this spring, it's going to start to move, and as I mentioned before, it goes fastest through equilibrium. But if it's going fastest through equilibrium and it slows down to a stop, that means it has to undergo some kind of acceleration. And so now we can take Hooke's law, since F is equal to negative K times the amplitude, and we can tie that into Newton's law. F is equal to ma. And then once we know these two, we can tie them together. And we can say negative Ka is equal to ma. And so if I know how far it is from equilibrium, if I know the amplitude from equilibrium, I can get the acceleration at that point. I can say A is equal to, what's this, K over the amplitude divided by the mass. So if it's 3 centimeters away from, if it's traveled 3 centimeters, then I can get the acceleration when the amplitude is 3. If it's 5 centimeters, I can get the acceleration when the amplitude is at 5. So that's a nice link between Newton's law and Hooke's law, because it is undergoing some acceleration. It has to, in order to speed up and then slow down and then speed up and then slow down. Alright, and so let's take a look at the next one. Once you force that mass up or you stretch it down, you have put some work into the system, which means you've given it energy. And when you've given it energy, it's stored as potential energy. So I'll call it energy of a spring. And the equation for energy of a spring is 1/2 Ka squared. And again, A is the amplitude and K is the spring constant. The unit for the spring constant, I didn't give it to you in the last video, is Newton over meter. And of course, that's got to be in meters. Alright, so once you stretch the spring and let it go, all of that potential energy in the spring is going to be converted into kinetic energy, especially it's all converted into kinetic energy as it passes equilibrium. And then that kinetic energy gets converted back into potential energy of the spring here. Then, because it stopped, which means that kinetic energy is 0, so potential energy has to be at max. Then it goes back. So we can find the velocity at right here at equilibrium, which is easy because we know that all the potential energy of the spring is turned into kinetic energy. So using conservation of energy, I can say that the energy of the spring is equal to the kinetic energy as it passes through equilibrium, which means that 1/2 Ka squared has to equal 1/2 mv squared. Once I know how far it's traveled, once I know maximum amplitude, I can solve for the velocity. That's through equilibrium, but what about halfway, or maybe when it's traveled 2 centimeters up, or maybe when it's traveled 8 centimeters up? How do you get the velocity there? Well, what most students want to do is they want to figure out what the amplitude is and take that number and place it in for A. So let's say the maximum amplitude is 10 centimeters, but I want to know what the velocity is when it's traveled 8. So most students will say, well, if it's stretched 10 and it's traveled 8, that must mean the remaining amplitude is 2. So I'll put that 2 there and solve for velocity at that point. But you can't do that. We have a squared component to deal with. So we have to do it a little differently. So I'll start from the beginning and say that 1/2 Ka squared is equal to 1/2 mv squared. And let me get rid of the halves for the sake of algebra and cleaning up the equation. Then it's K, and then it's a squared minus how far it's traveled, x squared. And that's equal to mv squared. So let's say the maximum amplitude, the amount it was stretched was 10 centimeters, but I want to know what it is when it's traveled 8 centimeters. So that would be 10 squared minus 8 squared. Then you solve for v. Or let's say the maximum amplitude, I pulled it as 6, but I want to know what it is when it's traveled 3 centimeters. So it becomes 6 squared minus 3 squared, and then you can solve for v. So that's how you find the velocity at any point in a spring, is if you know how far it is from maximum stretched or compressed. All right, once you do that, let's take a look at the period. Now the period is how long it takes to cycle. That is, how long it takes it to go, if I compress it, how long it takes it to go down maximum stretched and back up to the original position. That is the definition of the period, how long it is for one cycle. And the period depends on the mass and the nature of the spring, how stiff this spring is. So T, the period, is equal to 2 pi square root of m over k. And the 2 pi is there because it gives you that nice curve. So once you know the mass hanging on it and what the nature of the spring is, how stiff it is, you can calculate how long it's going to take a cycle to occur. That's the period. Now once you find the period, you can inverse it to get the frequency. And the frequency is how many cycles will fit in a second, how many times it'll go up and down, complete cycles, in 1 second. And in the last video, I said that the period is 1 over the frequency, and the frequency is 1 over the period. So once you get this number, the period, just inverse it. Once you inverse it, you get the frequency. You can do it that way, or you can turn this, you can inverse this whole original equation. And if you inverse this whole original equation, that means the frequency is equal to 1 over 2 pi square root of k over m. Either way you want to do it, it's up to you. But I believe only one of these is given on your formula chart for the test, and I believe it's that guy, but I'll check into it for you. All right, so that is a spring. Let's take a look at a pendulum. All right, let's see if I can draw a pendulum here. So I have a pendulum, and I'm going to pull it out some angle theta. That's the amplitude, that's the angle theta. And then it's going to swing down through equilibrium and over to the other side where it's the same angle theta. Alright. Now it turns out that the harmonic motion of a pendulum only occurs for small angles, small angle approximation. And it has to do with having the restoring force being proportional to the displacement. And that only occurs with small angles. So we're saying probably approximately less than about 15 degrees. Oops, I wrote that backwards. 15 degrees of a theta of 15 degrees. Small angle approximation. After that, anything above that, scientifically, when you use calculations, since the restoring force isn't proportional to the amplitude, then technically that's considered non-simple harmonic motion. All right. Well, when you start a pendulum, you put in energy again, and when you do, you give the pendulum height. And since this pendulum has height, what it has is potential energy, mgh. Okay, it's height relative to the lowest point, because remember I said the restoring force is associated with gravity. And so gravity is what gets this guy going, and then on the other side, gravity is what slows it down. Then when it stops, gravity is what gets it going, and then as it passes equilibrium, that's what slows it down. Which means as it passes through equilibrium, it's going its fastest. So at this point, I can use the equation mgh is equal to 1/2 mv squared, conservation of energy. And then I can figure out what the velocity is at the lowest point. Now the question is, how do you get that height? Well, the height is based on the length of the string. So let's call this L. So the length of this pendulum is L. And so this height here, which is adjacent to this angle, is L cosine. So the height becomes L minus L cosine theta. Because if I know this height and I subtract this height from it, then I know how far it's fallen. That's the H. That's how much potential energy has been converted into kinetic. So mgh, and why don't I expand that out to L minus L cosine theta is equal to 1/2 mv squared. So once you get it going and you find out how far it's dropped, you can tell how fast it's going when it passes through equilibrium. Well, I hope this helps, and I believe this is all of the equations. If not, I will give you some more in class. If you have any questions, ask me when you see me.